So you had to do some more modeling last night. What was the difference last night about the modeling you had to do? What was the difference? What was new, Macy? Yeah. More than linear and quadratic. Now what do you have? Cubic. Anything else? Quartic, I think. And power functions there. Power functions, those are really simple, cubic and quartic, going through the origin, those pictures we looked at yesterday. Are there any specific ones from the homework that you'd like to talk about? Any specific ones? Raise your hand and ask. Let's go. Justin, which one number?
18.
On which homework packet?
Homework packet 3.
18 on homework packet 3?
That's talking about the
yeah, okay. Sure. So 18 here. What does it mean by diminishing returns? What does it mean by diminishing returns? What does diminishing mean?
Decrease.
So yeah, so what do returns mean? What you get back. So what does diminishing returns mean? Decreasing what you get back. You just said it out loud. Okay. Diminishing means decreasing. Returns mean. So put it together and you get less back. What you get back is decreasing. What you get back is decreasing. You're getting back less and less. The numbers are going down. Okay. A study by the U.S. Office of Science and Technology in 1972 estimated the cost in $1972. The other thing you could do, Justin, if you don't know what this means, what's the easiest way to get what that means? 2 ways. You can phone a friend. You could use a dictionary. Or the internets. Look it up, okay? I don't expect you to know the answer to everything. I expect you to be able to find the answer to everything and know what to do with it. A study by the U.S. Office of Science and Technology in 1972 estimated the cost in $1972 to reduce automobile emissions by certain percentages. Reduction in emissions 50%, cost per car. Interesting. Find a model that captures a diminishing trend. So what would be the first thing you could do before you run a regression? What should you do first? Plug in the data into what? And do what with it first? What? Plot points. So let's plot points first. Data. Let's zoom stat. It's 9. Oh, I need to turn off. What do I have? I got to turn that off. Turn plot 1 on. Zoom 9. There it is. So it spikes up. What model do you want to try to use? Cubic? So stat, calc, cubic regression. And vars.
The correlation coefficient of the big one is the highest one?
I don't know. For some reason it's off on this. Let me turn it back on. It's in second catalog.
D.
You want to go to alpha. Oh yeah, alpha D. Oh, alpha is already turned on. So diagnostic what?
On.
Yes. Diagnostic on. Let's run that again. So stat, calc, cubic reg. So we have an R² value right there. Is that pretty good? That's a very good cubic reg. 0.994. That's good. And then we go back and let's graph this. It gives you the R² value. If your calculator is not giving you that R² value, it's because diagnostic is off. It's off by default. You turn it on once and then you should be set. The R² being closer to 1 is better. The closer it is to 1, the higher the correlation between the data. So that's a pretty good value. But if you want to compare it, we could run others. It's telling us that the question again. Let's go back up to the question that asks, find a model that captures a diminishing return. So if you had to round, go to at least 3 decimal places. So we have f of x is equal to 0.020 x cubed plus or minus, thank you, 3.880 x squared plus 247.675 x minus $5,163 and, or not dollar, yeah, like that. So if we want it, this was $1974, you'll notice you get a nice return. This is efficiency, right? Reduced emissions here. And then what's the y-axis? Cash, right? The cash spikes. So it seems like it might be a good idea to go all the way to here before it spikes. What point was that? Do you remember? On the table, it seems to spike after 80%. For $100, you can go 80%. It's not bad. Now, if you wanted to run a different model, though, let's run a different model. If we quit out of this, stat, calc. Let's try a different one. Quartic reg. Let's try quartic reg. The R squared value is, oh, we got to go down. 0.9. Oh, is the R squared, is that better?
Yeah.
Okay, you didn't say that. You just said that's not what you said. So yeah, now you go back and you try quartic. It seems that this is better than cubic. Are you going to be able to see much of a difference when you graph this? Not really. Again, why don't you really see much of a difference? Two reasons. The calculator resolution is, it's not very good. And also, how much, I mean, the correlation coefficient was better, but it was better by 2 1,000ths, right? So are you generally going to see much of a difference? Probably not. Yes. Is that a question? No. We could use this to estimate even further if we wanted to. If you wanted to predict in between. So if you wanted to predict values like in between right here or out here, you could do that. Any other questions from the homework?
So you're finding
which model is the best? Has the best R squared value?
What is, I still don't know what's capture the diminishing return trend.
You're capturing it. You're describing it. You're describing it.
Describing the
Captures, describing. Find a model that describes the trend. Find a model that describes this data. What model? Yeah, but you're diminishing returns, meaning for every time you go up 5%, it costs a lot more. You're getting diminished effect. Your dollar doesn't do as much. Okay?
Diminishing effect.
Yes, that's one way to think about it. Yep.
You're just asking you to describe.
To describe the data, yeah. But they want you to run different models. Now, Quartic was 0.996. Is that the best one?
I think it's the best one.
Well, there's other ones. The other one I want to try, which we haven't talked about yet, there's one right here, exp reg. Let's try that one.
What is the
Exponential functions. We're going to talk about that today. To do exponential regression, bars, y bars. Let's enter. What's our R squared value? Let's see. Ooh, R squared is not very good at all. So exp reg, I'll clip that in. It's not very good. Quartic seems pretty good.
I tried.
Did you try a few others?
I tried almost everyone.
And Quartic seems to be the best?
The Quartic is the best.
So this is exp reg, frowny face. Okay.
What is R?
R, just look at R squared, ignore R. R squared is what I want you to look at. Okay? What? It's used to calculate R squared. Like your bigger question is, where does R squared come from? We're not going to get into that in this class. Take AP Stats if you want to know that.
Oh, no.
Helpful. Macy, go.
You go up to L2 or L1.
How?
And hit
Where do I go?
Use the arrow up. Go to list.
Go to list. Oh, list. List is that blue right there, so second list. Yep. Is that what I want to do?
No, stat.
So stat. Yep.
Edit.
Edit. Yep.
Go up to L2.
Or L1. Yep. And do what?
Hit clear.
Yes. Hit clear.
Yep.
I'm hitting clear.
And go down. Hit down arrow.
Hit the down arrow. Ah. Clear and down arrow. That's a great tip. Okay, so we've cleared them. When you have a correlation like that, what does it mean? That's pretty perfect. That means there's some sort of law you need to figure out.
I would say, oh my god.
That right there. That circled the wrong one there. That right there would be called awesome.
Awesome.
Okay, that right there is pretty much perfect correlation. Perfect correlation. Well, yeah, it is perfect. I mean, the reason it's not perfect is it's rounded. So he predicted that there is an actual law. And what does part B ask in this question? Kepler, the square of the period of revolution of a planet is proportional to the cube of its mean distance from the sun. The square of its period. Which one is period, D or T?
T.
So this right here is period. It says the square of its period is proportional, meaning it is some factor times what? the cube of its mean distance. Which one's mean distance?
D squared.
D squared. D squared. The cube. Oh, sorry, cube. You're right. Yep, the cube. So it's saying that t squared is equal to some constant times d cubed. Let's go back and see what we have here. We have our relationship right here relates, what did we put into the x? We put in d. So it was dt, right? So this is t is equal to something in terms of d. So we have t in terms of d is, what was a? 1.0003 times what? D to the what power? 1.49966. That's pretty good, right? So what do we have? T is equal to d to the, what can you round that to pretty confidently?
1.5.
And the coefficient is 1. Is that pretty cool? Coefficients of 1 are great. Well, here's the thing. I don't really like 1.5 power. How do I get rid of 1.5 power if I want to make it a whole power? Well, that would be, yeah, so t equals d to the 3 over 2. If I wanted to make that a whole number, what do I multiply by to make that a whole number? What's the easiest thing to multiply by? Yes, or let's square both sides. If I square both sides, look what happens. T squared is equal to d what? Cubed. So did we just verify Kepler's law? Yeah. In this case, what is the coefficient? What's the constant? What's in front of d? 1. It's 1. So t, the period, is equal to d cubed. It's pretty cool. So did we actually verify Kepler's law?
Yeah.
That kind of correlation coefficient right there means there's some sort of law in effect. Look at that. That's tens, hundreds, thousands, 10,000s, 100,000s, million, billion, right? It's 3 billionths off in correlation coefficient. Is that pretty perfect? Yes. That's excellent. For Germany, using those 5 data points, let's predict that. Where do we want to predict the population to? 2025? Let's see that. Let's see if we can do that. So do that right now. See if you can predict it any way you want. No talking, any way you want. So let's quit out of this.
Which year are we going to predict?
So we're going to do 2025. So
2020.
so the way I did it, so I'm going to plug in 25. So if this trend continues, depending on your model, it could be different. It could be different. Linear, generally populations aren't so linear. This is amazing because when we ran this regression, let's do that second entry. We ran this regression. We ended up with, is that a ridiculous correlation coefficient? That's a ridiculous correlation coefficient. Ridiculous. That's pretty cool. Okay, so want to stay with population? Let's stay with population. Let's go back to that site. This is World Bank. That's nice. So what country do you want to do? Oh, look what they have over on the right here. Look at the right-hand column. The general trend. Isn't that cool? So what do you want to look at? The U.S.? Let's look at the U.S. United States. United States.
How do they drop 30 million in 20 years?
Oh yeah, easy.
So I don't know if I get that number. Everyone gets 5 points. Yeah.
Okay, here we go. So it's 05, 06, 07, 08, 09. Let's go to 2025. So what do you have to do first if you're going to do this? Clear your lists. Please do that. So I clear my list. Let's go up, stat, edit, clear down. Oh, I didn't have to clear that. 5, 6, 7, 8, 9. 2, 9. What do you think the most common error people make on this is?
The little mistake, like.
Yeah. What happens if you put in like an extra 0?
Yeah.
Sometimes the model will hold a little bit. Global population is growing. What number did we just hit?
9 billion.
What? Global population.
Yeah, 9 billion.
7 billion. I'm gonna run the. We liked quartic regression, huh? See what it looks like. Our correlation coefficient is 1 again. So we graph this. Oh, well, it's not going to graph very well. Why? Because I haven't zoomed what?
The quartic is 1 again.
That's a pretty good correlation coefficient, huh?
It's
Wait, is that my data? Is that correct?
No. No.
Something's wrong there, huh? Stat, edit, 295. Did I make a mistake? I think I probably 295. Oh, look what I forgot on that number. 295 753 0 0. Oh, gotta actually type it in, I guess. 295 753 0 0 0. And now I'm gonna go back. I'm gonna enter that. Quit out. Second entry. I'm gonna run it again. And now I'm gonna do zoom. So can we make a pretty accurate prediction of where population's going, barring any major events?
Yep.
Yeah, so we go back out of this. We're going to do y1 at 25, I said?
Wow, 1 7.
Does that look like it's going to... Do we? So do we think we're going to have... Hold on. Let's look at our function here. I'll change the mode here. Mode, so you can see the whole number. Classic. Go back to y equals. Whoa, hard to see that. One thing that we should check first, let's check the table of values. Are they all the same number of digits? Yeah, E8. You see the E8 right there? So that's good. So then I did stat, calc. I'm going to do cubic or quartic? Quartic, okay. Vars, y1. Enter. Zoom 9. So that's it right there. So if we go out of this and we want to do y1 at what? 25, right? What do you end up with?
Why I get 177700000. I got it too.
You got different answers?
We all just round.
You got that number. It's gonna. This is where it depends on the calculator model and the operating system. So you're gonna get slightly different answers. Anyway, is it about the same? But what's interesting about this is how big is that number right there? It's 1 billion people.
More than China. Oh, I want to see China.
Yeah, China. Yeah, let's want to do China now. Okay, so this right here is. Let's just look at this. This is almost 2 billion people in the United States alone, if we keep at this population growth rate. Now, that's based on 5 years of data, right?
Yep.
What would be a more accurate model if we looked at 20 years? Let's look at it. We could look at a bigger one. I like these 5-year estimates because they're actually pretty accurate. It's actually kind of a neat thing to look at. China.
Oh, it's been scared me, I guess.
China. Here we go.
30 billion.
Yeah. Let's make an estimate based on 5-year model. Okay, 5-year models are not the best, but based on this 5-year model, let's see what China's going to go to. Okay, here's China, everybody. So that's China right now, everybody. China right now in 2025. Who has a number for me? In 2025, by the 5-year model, can you tell me what it is? Someone give me.
7371900.
Stop! Kids, figure it out. That's not the best way to answer a question. Hanley, 73719, yes?
0000.
Like that?
No, 40.
4 zeros?
That's less.
Yeah, that's less.
So can someone actually give me a number that makes sense? That would be great.
I got that too, though.
So what is it?
Yeah.
7 what?
737.
Yep.
190.
Yep.
000.
Like that? So we end up with 730. Okay, guys, I don't understand. Yeah. So, what's the problem here? This actually, you're correct. Your model. What's wrong? Yeah.
The quartic events eventually go down.
It changes direction, right?
Yeah.
So for this section of the quartic, it was very accurate. But in the future, this model turned down when the population is actually going to keep going up. So even though the coefficient is really good for that, it's not good for future. So try running this. Try expreg on it. You just did quartic reg, right? We just talked about it earlier today. It's in your calculator. So try expreg and tell me what the said there is. Even though China has way more people, it's growing at a much slower rate relative to its current population. Population growth, apparently in China, is slower than it is in the United States. So in 25 years, our growth rate will push us way past. But is that necessarily true? To make this model more accurate, what will we need to do? Look at of what?
Much more data.
We need more data. We look at more data. Our actual population in 2010. Let's see what the population actually is. 307. It's interesting.
But it's not.
What does that mean?
It's going fast.
It's our growth, our rate of increase is increasing. Okay, your homework tonight, everybody, is this. Find, analyze, and bring in at least 2 cool data sets. You understand what that means, everybody?
Yeah. So like do the thing we did today.
Do the thing we did today, but try to pick some interesting data.
Alright.
Pick something cool. Sports, economy, anything you want.